we are going to say that this function has a maximum at AB if the value of the function here is bigger than the value of the function for all points around AB. So if we evaluate the function f at some point around, we are going to have a lesser value. In any point around the maximum, we are going to have a value that is smaller, that is less than the value of the function exactly at AB. So we are going to say then that the function has a local maximum at AB if the values at the points around AB are always less than the value of the function at AB. So that will define then what is a local maximum of the function. In the same way, the function will have a local minimum at the point AB if for the points around AB the value of the function is always greater or equal than the value at AB. So the value at AB will be the minimal possible. All the values, this will be like the smallest one. All the other values will be bigger than the value at exactly AB. A generic name for maxima and minima is extrema. So we can say, if we say that the function have an extremum at AB, means that have either a maximum or a minimum. And maxima and minima are the plural of maximum and minimum. We're going to say that a point AB is called critical if the partial derivatives are zero. So remember that for functions of one variable, if the derivative is zero, so we have that in this point, we can have eventually a maximum and minimum, but not necessary. Well, this is going to happen in the same way for functions of several variables. So we are going to call critical if all the partial derivatives are zero. And we have a theorem that tells us that if the function has a local extremum at AB, meaning has a minimum or a maximum, then AB is a critical point. So this theorem is telling us that if there is a minimum or maximum, so then the derivatives are zero. But this is an if-then result, meaning that we cannot read it in this direction, right? So the fact that the partial derivatives are zero does not guarantee that the function is going to have a minimum or maximum. In fact, these points, the points that have derivatives actually equal to zero but are not minimal or maximum, are going to be called saddle points. So if you remember the inflection points in the functions of one variables, this is going to be the analogous to that. So a point in which the derivative is zero but is not a maximum or a minimum. So the saddle points are going to be then the points in which the partial derivatives are zero, meaning it's a critical point, but they are not a minimal and they are not a maximum. The critical points are the points in which the partial derivatives are zero. So in other words, are points that we can calculate by solving the equations partial derivative respect to x equals 0 and partial derivative respect to y equals 0. So we should be able to calculate the critical points. But once that we have all the critical points, so we know that they may be maximum or minimum, but we don't know that. They may be also saddle points. So this second derivative test is going to tell us, or is going to help us to decide what are actually these critical points that we can calculate just by the definition of critical point. But first, we define what is the Hessian of a function, which is the determinant calculated in this way. Actually, the Hessian can be written as a determinant to remember to remember this formula by just putting the second derivative respect to x and respect to y like this, and in the other two entries we are going to put the mixed derivative that is the same, right? So we put the same sign there. So the determinant calculated in this way is going to give us what is called the Hessian of the function at the point A, B. And this Hessian is going to be very relevant in order to decide is a critical point, is a maximum or minimum or a saddle point. And that is going to be given by this theorem. This theorem says that if all the partial derivatives are continuous around the point A, B, so then we are going to look at how much is the Hessian. I mean, this Hessian, since it's evaluated at the point, at the critical point A, B, so it's going to be a number, right? So it's the result of a determinant where all these things here are numbers, so the Hessian is going to be a number. So we have to check if this number is positive or negative. That's the first thing that we have to check. If this number is going to be positive, I mean, if we got that the Hessian is positive, so then we can say directly that the function is going to have extrema there. It's going to be a maximum or a minimum, but it's going to be extrema for sure. So it's not going to be a saddle point. Okay? So Hessian positive, extrema, and Hessian negative, saddle point. And in case that the Hessian is positive, I mean, in case that we have extrema, moreover, we can decide if this extremum is actually a maximum or a minimum. And the way to decide is to look something further. We have to look now to the sign of the derivative, the second derivative respect to x. If this derivative is negative, we're going to get, I mean, if it's negative down, we're going to get that is a local maximum, something that looks like that. And if this second derivative is positive, like this, so then we are going to have a minimum. So if the first thing that we check is that if the Hessian is positive or negative. If it's positive, extrema. If it's negative, saddle point. And if it's negative saddle point, it finish there. But if it's positive, we want to know what kind of extrema is maxima or is minimum. So in order to decide that, we look at then at the second derivative respect to x. And in case that the Hessian is equal to 0, well, the theorem doesn't say anything in that case. So this test is not good for that case. We need to decide what is that point by other methods, but we cannot decide by this theorem. See in an example how do we actually apply all these results to actually calculate the local maximum, minimum, and saddle points of this function. So this is an example. Let's consider this function of two variables, and let's start then the first step of calculating maximum, minimum, saddle points will be the calculation of critical points. So to calculate critical points, first of all, we need to calculate the partial derivatives, right? The partial derivative respect to x, in this case, is going to be equal to minus 6x plus 6y. And the partial derivative respect to y is going to be equal to minus 6y squared plus 6y and plus 6x. So these are the two partial derivatives. Now, by definition of critical points, we need to find when these ones are equal to 0, right? We have a system here of two equations that we need to solve it. So from the first one, from the first equation here, we get that 6x is equal to 6y. So in other words, x is equal to y. So if x is equal to y, we substitute in the second equation, and we get that minus 6x squared plus 6x plus 6x is equal to 0. Solving this equation, we get that 6 plus 6 is 12x equals 0. So we take minus 6x as a common factor, x minus 2 equals 0. So the two solutions here will be minus 6x equals 0, which gives us x equals 0, or x minus 2 equals 0, which gives us x equals 2. So then, if x is equal 0, then coming back to this equation, we get that y is equal 0, and we have the first solution of the equation. That will be 0, 0. And if x is equal to 2, so then substituting again here, we get that y is equal to 2. And we have the second critical point, 2, 2. So this is then the set of critical points. What we can say that are candidates to be either maximum, minimum, or saddle points. And in order to decide what they actually are, we are going to apply then the method given by the theorem based in the calculation of the Hessian. So we retain here the derivatives, that is what we are going to need to calculate the second derivatives, and so we don't need any more these calculations. So then, in order to calculate the Hessian, we need to do the second derivatives of these functions here. Okay, so the second derivative here, if xx is going to be the derivative of this respect to x again, is going to be just minus 6. And if yy is going to be the derivative of this respect to y again, so this is going to be minus 12y plus 6. And then the mixed derivative, fxy, we can calculate starting with any of them. So for instance, we can calculate starting with this one and calculate the derivative respect to y. And so the result is going to be 6. Okay, so these three things is what we need to calculate the Hessian. So let's calculate the Hessian at a generic point xy. This is going to be the determinant where we put in the diagonal the derivative with respect to x and y. So it's going to be minus 6, and this is going to be minus 2y plus 6. And so in here and here, we're going to put the mixed derivative. So in this case, it's 6, so we're going to put that number there. Okay, and now we calculate this determinant. That will be, in this case, minus 6 times minus 12y plus 6 minus this product that is 36. So we do the operations here, and we get that the Hessian is minus 6. We take minus 6 as a common factor, and we get here minus 12y plus 6 plus 6, let's say plus 12. So taking 12 also as a common factor, we get here 72 times y minus 1. Okay, so this is the value of the Hessian. For any value x, y, the Hessian is equal to 72 times y minus 1. And so now we look at our collection of critical points, and we check how much is the Hessian for each of them. So let's calculate, for instance, the Hessian now for the point 0, 0. So let's evaluate that 0, 0. So x0 and y0. So that will be 72 times 0 minus 1. So this is minus 72. So the Hessian at 0, 0 is minus 72. That means that is negative, right? That's what we wanted to check, if it's negative or positive. It's negative, so automatically we can say that 0, 0 is a saddle point. And now we do the same with 2, 2. So let's see what 2, 2 is. So let's calculate the Hessian now at 2, 2. That will be, plugging in here, 72 times 2 minus 1, so this is 72 times 1, which is 72. This is positive. So that means that this is going to be an extreme, meaning this is going to be a minimum or a maximum. So we can deduce here that 2 is extreme. Is extreme, but which one is? Is a maximum or minimum? So we need to decide that by checking at the fxx at 2. So we look at this derivative. This is just minus 6, constant at any point. This is minus 6, so it's negative. Remember that if it's negative, so then it's going to be a maximum. And so we can say that actually we know what extreme is now, and we can say that this is going to be actually a maximum. And so we have the 2 points in these functions where these things are going to happen in the graph. So at 0, 0, we are going to have a saddle point, and at 2, 2, we are going to have a maximum of the function. And then we can also, since we know that it's a maximum, we can be interested in knowing what is the maximum value. You see that are different things, right? Maximum is where it's a maximum point where the maximum occurs, but the maximum value is to evaluate the function at the point. So we can look at the original function that is given here and find out how much is the function at the maximum. So at 2, 2. So we plug in here, and we have minus 2 times 2 cubed, so that will be 2 cubed is 8 times 2, 16, with a minus in front is minus 16, minus, we keep evaluating here, minus 12 plus 12 plus 24, so this cancel, 24 minus 16 is 8. So the maximum value is going to be then 8. So if we see the graph of this function, so it's going to be at the height of 8, where we have the this local maximum. Let's take a look actually at the function. So let's graph the function. This is the expression of the function that we have, and this is the graph that we obtain in Sage. So let's look at this function from different viewpoints. We have, because we can see it from all directions, we can understand also how a saddle point looks like. So this is the saddle point that we are getting, and this is the maximum of the function that we got. So the saddle point, you see that if we look at in this direction of the function, it looks like it's a minimal, right? But if we look at the same point from here, it looks like it's a maximum. So this is because in some directions, so in the saddle point here, there are points whose value is less than the value at the saddle point, and there are points whose value are more than the value at the saddle point. That's something that does not happen at the maximum, right? At the maximum, all the values of the points around the maximum will be around here. So if we take any point in a neighborhood, so the values will be always less. So the maximum value here is 8. So that here is minus 50, here is 50, so here is 40, sorry. So around here will be 8. So all the values we calculate around will be values less than 8. So we can visualize here then the local mean, the local maximum that we find, and the local saddle point. So all what we have calculated so far are local things. Local minimum, local maximum, meaning that is the highest point in a neighborhood, let's say locally. But if we look, for instance, in a function, it may have several maxima values. So if all of them, there is one that is the biggest one, so that is going to be the absolute maximum. But also, that is about the points that are inside of the domain. But also, when we have that the function is defined in a closed and bounded set D, we have that this function necessarily will reach an absolute maximum and an absolute minimum at some points in the domain. So these points could be in the interior of D, that would be some of the critical points, or could be in the boundary of D. Then, to calculate the absolute extrema of the function, we're going to start by calculating the critical points and evaluating the function at the critical points, but that will be not enough. So we're going to also need to determine what happened in the actual boundary of the region. We consider this region D in the domain. I'm going to draw just the x and y axis. The x vary between -1 and 1, and the y vary between -1 and 1. So this is the domain here where we are going to calculate the maximum and minimum. So this maximum and minimum, it may happen in points in the interior, or it may happen in the parts of the boundary. So we are going to start by calculating the critical points, and then after that we calculate what happened when we restrict the function just to the boundary. To calculate the critical points, we start by calculating the partial derivatives. The partial derivative with respect to x is going to be 2x minus 4xy, and the partial derivative with respect to y is going to be 8y minus 2x squared. And so, in order to calculate the critical points, as before, we need to solve the system of equations of both partial derivatives equals to 0. So from the first one, we get that 2x times 1 minus 2y is equal to 0, meaning that 2x is equal to 0, which gives x equal to 0, or 1 minus 2y equals 0, that makes y equals 1/2. So then, if x is equal to 0, for the first of the solutions, we substitute here and we get that 8y is equal to 0, and then y is equal to 0. So this is going to be our first critical point, 0, 0. And then for the other one, when y is equal to 1/2, we are going to have that 4 minus 2x squared is equal to 0, which means that 2x squared is equal to 4, x squared is equal to 2, x is equal to plus minus the square root of 2. So then we have here two more points. So square root of 2, 1/2, and minus square root of 2, 1/2. So these are all the interior critical points. Though, when we check the region that we have, it was x and y between -1 and 1. So then actually these ones are not in the interior of the region. So because square root of 2 is 1.4, right? So we eliminate these critical points, and the only one that falls inside the square is going to be the critical point 0, 0. So this is the first one that we are going to keep. We're going to keep the point 0, 0. So let's evaluate. So f at 0, 0 is going to be equal to, we go to our function and calculate the value at 0, 0 is going to be 0 minus 0 plus 0 plus 4. So the value of this function is 4. And this is the first value that we are going to collect for our comparison at the end with all the candidates to be maximum and minimum. Okay, so we finish with this, with the part inside of this domain. So now let's see what happens when we go to the outside. So this is our domain, and now we are going to start studying what happened in the boundaries. So when x is equal 1, so if x is equal 1, so we are going to restrict this function of two variables to the region where x is equal 1. So it's going to become a function of one variable. And we're going to have that fy, if we put here in all the places where there is an x, we put x equal 1. So we're going to get that this is equal 1 minus 2y plus 4y squared plus 4. Combining like terms, this is 4y squared minus 2y plus 5. So this is now a function of one variable, so we are going to calculate just the regular derivative of this function, of this parabola, which is 8y minus 2. And then we find out when this derivative is equal to 0, and we get that this happens when y is equal to 1/4. So then we have here another of the points to investigate. 1/4. So let's add that to our list. So evaluate f at 1/4. So we plug in here x equal 1, y equal 4, and so we get that this is equal to 1 minus 2 times 1/4 plus 4 over 16 plus 4 equals 5, right, combining like terms, minus 1/4, which is 20 minus 19/4. So this is the value, then 19/4 at the point 1/4. So let's just keep this value for future comparison. And so we know that the evaluation here, the result was 19/4. Okay, so we continue with the remaining of the boundary. So what happened here? So now we have to put here the value y equals minus 1. Well, it happened that when we substitute here by minus 1, we obtain the same thing, right? Because in this case happens to be a square, so we're going to get the same thing, and so the value is also 1/4. So this is our next point, f of minus 1/4. When we plug in, substituting x by minus 1 and y by 1/4, we obtain the same thing. So we got that f at minus 1/4 is equal to 19/4. Okay, so now we go to the points in the two horizontal segments of this domain. So let's see what happened here, for instance. So that will be when y is equal to 1. So we substitute and we got that f of x, again, is going to be a function of just one variable, equals x squared minus 2x squared plus 4 plus 4, which is minus x squared plus 8. We do the regular derivative of a function of one variable, and this is equal minus 2x. We make this one equal 0, and we get that x is equal 0. That's our next point, 0, 1. Let's evaluate the function at 0, 1. And we obtain that the result is 0, 0, and so here 4 plus 4. So the result is 8. So this is the next value in our list. F of 0, 1 is 8. Let's continue. The other segment here. So that will be when y is equal minus 1. So now let's substitute. For this case, when y is equal minus 1, we get that the function is x squared plus 2x squared plus 4 plus 4, which makes 3x squared plus 8. We do the derivative of this, and this is just 6x. We make it equal to 0, and we get that x is equal 0. That is then our next point, and we evaluate, and we get that f at 0 minus 1 is equal to 8 again. Okay, so with this we finish what happened at each of these segments. It remains to see still what happened at the intersection points. The first one, that will be 1, 1. So we have that f at 1, 1 is equal to, we substitute here, right? X equal 1, y equal 1. So we get 1 minus 2 plus 4 plus 4. We got 7. And then we get f at, the next one will be minus 1, 1. And so we get here 7 again. And then this one here, that will be f of minus 1 minus 1. So we obtain here 1 plus 2 plus 4 plus 4, which is 11. And the last one will be f of f of 1 minus 1. So that will be 1 plus 2 plus 4 plus 4, 11 again. So this is the list of all our values. So the possible, the candidates to be extreme are going to be possible values 7, 7, 11, 11, 4, 8, 8, 19 over 4, and 19 over 4. So we just have to compare them and decide what is the smallest and the biggest one. Well, of all these numbers here, the biggest one is 11. So the maximum is at these 2 points, this point and this point. So we can write down that. So the maximum is going to be at minus 1, and also at 1 minus 1. And the value of the maximum, so the maximum value is actually equal to 11. And for the minimal number here is 4. So the minimal happens at then 0, 0. And the minimal value is going to be 4. So this is then the absolute maximum and absolute minimum calculation. We observe that in this case, we are obtaining that the minima happen at 0, 0, it's an interior point, though the maximum is happening at this point and at this point. So it's happening at a point in the boundary. So these are the possibilities. Sometimes will be all inside, can be inside or on the boundary.